Okay, so I'm going to go back to sort of more classical reactive synthesis. And here the title is Simplic Finite and Infinite State Synthesis. This is joint work with Sean Sopati, Luca Di Stefano, and Gerardo Schneider, but Sean's name is highlighted here because he's really the main contributor, and he, even the presentation is his, and I just... Because he's looking for a job, right? And he's looking for a job as well. But this, yeah. So I didn't declare my policy, but yeah, I strongly recommend. Yeah. So this is more or less my main contribution to the presentation and adjusting it to the audience. So we talked a bit about LTL synthesis. We talked a bit about the algorithms that are involved, and we've seen that there's an ongoing competition, and this is about so for finite state synthesis. And when we discussed the competition, I sort of sneakily talked about the issue of what happens if you have an arena plus LTL. And this in a way goes back even to, well, to the reasons that we suggested GR1. The way we were thinking about things when we were suggesting GR1 was, so we have some kind of safety conditions that are there, and then there's a liveness on top of it, so somewhere in the background. And also early work in robotics and in software engineering that talked about how to use synthesis for these things. They had a distinction between an arena and the goal and an LTL goal, and we sort of forced them to work on direct LTL synthesis. We don't allow them easily to encode the arena. And there has been work by Shahar Maoz, Fabio Somenzi, Gerard Altman, and others on how to incorporate better an arena. So quite a lot.
Also in the planning community.
And yeah,
the planning community. I mean, one of the recent best dissertation award was given for work on exactly on arena plus LTL.
Okay. Yeah. So I'm not alone here. But in this work, we consider what happens if the arena is infinite. And this has to do, well, there are decidable classes, and Igor is not here today, but I think he was one of the first to consider this and showed what happens if the arena is produced by a pushdown automaton. But here I'm more talking about things that are generally undecidable, but still see if we can do something. And a lot of people here have worked with it. So Bernd, Rusika, Asade, and especially Raina, who is going to talk about a very similar result tomorrow, that as far as I know has been developed independently from ours. So this has, and yeah, maybe this is a good time to say, we've been trying to publish this for over 2 years now, and we're not managing yet. So what are we doing? So as mentioned, we have an arena, and this is a bit complicated, but the infiniteness comes from these variables. So there are, they could be integers, they could be reals, whatever. But the control is a bit different from what other people have done. We have the classical, in a way, setup of synthesis in that we have a set of Boolean variables for input, a set of Boolean outputs, a set of Boolean variables for so these are environment, this is controller, and then the variables themselves, they react to this. So there's a fixed arena that says, this is how the variables start, and based on these fixed branching decisions by the environment and the controller, this is how these variables are updated. And at the end, we will have some kind of finite representation of how these variables are updated, but I don't want to go to really talk about this. And the full game says we have this arena, how the variables react to how the inputs and outputs from the environment and the controller. And we have an LTL objective that can talk about, obviously, the Boolean inputs, but it has also some predicates over these variables that determine the satisfaction determine the satisfaction of the formula. And the setting is pretty much the classical setting. We have an input from the players play sequentially. We have an input from the environment, choice of values for all these Boolean variables, and we have a reply by the controller, a choice for the value of all these Boolean variables, and then the arena updates the variables based on these choices deterministically. And the trace is the continuation or the evolvement of the valuation and how the Boolean variables are changing over time. And yeah, and then essentially we're talking about this is some kind of translation of realizability and unrealizability to this model. And here, in general, if these machines are allowed to be infinite state, then we get the classical distinction between realizable and non-realizable. So everything is determined. There exists either a strategy or a counter strategy, and yeah, and essentially we want to get, in the case that there is a finite state strategy, we want to get this Mealy machine at the end. Yeah, that's, and oh, yeah, as mentioned, in general, this is undecidable, right? So we have the variables are infinite state, and generally this is undecidable, and there's no way around this. So let me give you an example. This is more or less the systems that we're talking about. We have we have two integer variables. This is an elevator. We have an environment that sets the target of the elevator, and we have a system that sets the floor of the elevator. I omitted the variable that talks about the actual state according to that determines what happens, but essentially in this state, the environment chooses where to go. So it keeps the door open, and it just either increments the target or decrements the target. And at some point, it decides, okay, it's okay for the elevator to go. It closes the door, and then it's the role of the system to choose whether to go up or down, or to stutter, And we don't allow the environment, yeah, and then it should, at some point, should get to a point where it reaches the target. The environment opens the door, and that's it. It completes its goal, and we start again. And this is a combination. So this is the arena, but we also have LTL doors. Sorry, LTL specifications. And here, in order to make sure that this is really meaningful, we have to say, well, the environment closes and opens the door infinitely often, and without that, we can't really do anything. We want to make sure that we never move when the door is open, and always eventually we need to get to the floor. Floor is the target. So this is the kind of systems that we want to work on, and we want to sort of synthesize a policy for this. And yeah. And the approach is a Seeger approach. It's a bit hard to see here, but there's an abstraction, and all this thing here is the counterexample guided abstraction refinement. So there's this loop here is the refinement, and essentially we have some predicates that we know about the program. We build from that an abstraction of the program. We translate it to LTL, and then we have a finite state synthesis problem that essentially says the abstraction implies the satisfaction of the formula. And this is a sound abstraction. So if we get a controller for that, the answer is realizable. If, on the other hand, we don't get a counter strategy, then, and this is one thing that the specialized settings allow us to significantly change what people have done before, and we can plug this into model checking of the counter strategy against the program. So this sort of streamlines all the comparison between essentially the counter strategy and the program. If we get a counter strategy, counter example here, then there's the classical safety refinement, which goes back to the work of Rupak Tom and Ranjit, who had the sort of the setup of how to do safety refinement in the context of infinite state systems. But the new thing, another new thing here is that we also do liveness refinement, which is motivated by work of Penueli, Balaban, and maybe Tsuk about, model checking for model checking software. So we have something called liveness refinement, and based on that, we go back to the abstraction and repeat this loop again. Yeah, so this is sort of obvious. We start with our program. We look on the predicates that appear in the LTL formula. So we need to know that whether the floor and the foreign target and the same. This is something that we need to follow, and we create an abstraction that updates this predicate based on the real actions that are happening here. And we get things like, well, if we're in S0 and the floor is the target and the environment increases, then in the next state, the floor is going to be smaller than the target. But we also get non-determinism. For example, if we're in S1, we knew that we were before the target and we're going up. So at the next stage, we'll either stay under the target or they will become equivalent. So we get some kind of non-deterministic transition system, which we have to control. And so the abstraction is pretty straightforward. This is existential abstraction, and it soundly abstracts the concrete behavior of the program. And as we add more and more variables, it becomes closer to the behavior of the program. Technically, we don't use the predicates themselves. We add Boolean variables that enlarge the program, but this is sound. So we build an LTL formula from this abstraction, and essentially if the abstraction of the formula implies the abstraction of the program implies the formula is realizable, and then essentially we get the Mealy machine that we want. If this is realizable, then this is realizable in the real system. And the problem is what to do when this is unrealizable. So here we get to this kind of model checking problem. So essentially, we're getting some kind of Moore machine that represents what can the environment do in the finite abstraction that we have right now. We take that, and essentially we build a combination of the program and this counter strategy. There is some kind of simulation relation going behind the scene, but at the end of the day, we build some invariant that says, based on the choices that are made, based on the choices that are left to be resolved, we can encode this as an invariant problem that essentially checks, are the values of the predicates and the predicates themselves agree on what the program is going to do. And if this invariant can be model checked, if this counter strategy, the combination of the program and the counter strategy satisfies this invariant, then this is a real counter strategy. And yeah, and then we're done here. But in general, this is undecidable, right? So this is software model checking. So we delegate this to software model checking on this infinite state program. And yeah, so this is unrealizability. However, if there's a problem with the abstraction, we are guaranteed to find a counterexample, right? So, and this is actually a semi-algorithm. So the distance to the violation of this invariant, if it exists, is finite, and then we'll get a counterexample. And now with this counterexample, we can do two things. One is the classical safety refinement. So we have a counterexample. We'll build a formula that says, how does this lead to the thing that goes wrong? Use interpolation, get more predicates, and refine here. And the new thing is that we have two types of liveness refinements. And one is we get a counterexample that corresponds to a loop in the counter strategy. And in this case, we try to find that we try to prove that this loop is terminating. And essentially, we can say this sequence of actions, if you repeat it, leads to termination. And so extend the LTL formula by essentially saying this can't happen forever. And dually, if we have a ranking function that that can be used to prove termination of this counter example, then we can basically add the changes of this ranking function again into the LTL specification and ask again. If we go back to the safety refinement, this is not very surprising. We have the counter strategy. Sorry, we have the counter example. At the end, we try to, we start from a concrete value. We increase the value, but we get that actually they should be, the target and the floor should be equivalent, but they're not equivalent. We interpolate on this and we get, well, you should check, you should also follow whether the distance between the floor and the target is not only greater or equal than 0, it should be also greater or equal to 1. And if we continue doing this, essentially we will get non-termination. So this will essentially enumerate all the possible distances between the floor and the target. However, if we take the core of this counter example and we identify that it corresponds to a short concrete loop that says increase the target and then try to increase the floor while maintaining the target under the floor, we convert that into a program that essentially says, well, tries to do this, check whether this program terminates. Obviously, this program does terminate. And based on this termination, we can add constraints to the LTL formula that essentially say, if you continue, if you are in locations that do these kinds of action and they do this kind of action repeatedly, this will eventually terminate. So the only way for staying always in the loop is if you stutter inside the loop. So the LTL formula has some kind of information that says the only way for this to not terminate is if you don't increment here. So this is slightly more general than what we see there, but it's good enough. And essentially by two, so if we go back to our elevator example, we need to say if the target is below the floor and the other way around. If the target is above the floor and you increment, this will terminate, and the other way around. If the target is under the floor and you decrement, this will terminate again. And by getting these two sort of termination argument, we can handle this example, but we can also handle more complicated loops that have multiple steps and multiple transitions. And this is just looking on the structure of the counter strategy. If we have a ranking function, essentially we need to follow what happens along transitions. So if we need to follow how does the value of this ranking function changes along every transition, we add sort of predicates that follow this. And then essentially we need to say, if it decreases infinitely often, then it must either increase infinitely often or violate the invariant if there is an invariant on this ranking function. And what we do in many cases is just try out things that could be ranking functions. So we find things that appear in the predicates and that look like they're likely to lead to these ranking functions, and we just automatically add them. And this is, well, although we call it acceleration, sometimes it doesn't accelerate, but rather slow down. But so, yeah, so do that. And then overall, together, well, this is sound. Whatever both kinds of abstraction maintain soundness. If we get a strategy, then this is a sound strategy, and we can just use it. If we can prove that the counter strategy simulates the real program, then this is a real counter strategy, and we can stop there. Or otherwise, we make progress. So we always can make safety progress, but sometimes we can also make liveness progress. And in particular, if the program is initially finite, if the program is finite, then we are sure to terminate, but this is not surprising and depends on the size. And we also evaluated this. The evaluation is the only thing that sort of changed over these period, and in particular, once the paper of Raina and her co-author appeared, we also compared against them. These are not all the tools that do infinite state model checking, but infinite state synthesis, but based on comparisons of Raina's comparisons and comparisons that these two tools had with previous tools, then these are supposed to be the best. And indeed, so before the indeed, just a few more details. We implemented only linear arithmetic problems. So we didn't linear integer arithmetic problems. We don't support real values. We use a plethora of tools for everything, right? So Strix for LTL synthesis doesn't support the arena, enumerative encoding, so this is quite problematic for us. NewSMV for the model checking, CPA checker for termination, and MassSat for interpolation and for checking and SMT solving. And as you'll see, we either try with acceleration or without acceleration, and sometimes it does accelerate, sometimes it doesn't accelerate. One major difference between our approach and other approaches is that other approaches allow infinite branching for the environment. So it's perfectly feasible to say, give me an integer. The environment should give me the value of an integer. We have bounded branching, so fixed bounded branching. And we have a way of encoding this for linear arithmetic, but we don't have a way of encoding the continuous branching of real variables. But all the examples that we found for linear arithmetic essentially can be handled by this conversion. So this is not a real problem. And then so we collect interesting benchmarks from the literature. We add some of our own. And one interesting thing is that some of these benchmarks, we also try to make finite states. So we say these integer variables reach only to a certain threshold, and we try to see how does this work in the infinite state. And just like others, very simple, very small benchmarks, we don't use, and because if they just synthesize immediately with no need for refinement, then we just don't evaluate on them. And yes, and I think this is a very, very large table. Let me say, a few things. So we don't have cases where we distinguish between synthesis and realizability. So either we synthesize or we don't do anything. Okay? So there's no separate result for realizability versus synthesis. If we terminate, we have a strategy, and this is not the case for others. In particular, this small number here essentially says realizability checking works, but you can't extract a strategy. So enumerate, so somehow building the strategy doesn't scale. But otherwise, they kick our butt. So in terms of time, they're doing a lot better. So time is a problem. On the other hand, on these finite state experiments that are artificially bounded, we see that we sort of get constant runtimes, right? So as we increase the size of the problem, the same abstraction or a similar type of abstraction works for these finite state problems, and we get more or less the same running time regardless of the size of the parameters that we're allowing here, which is not true.
But which column is your tool?
S accept and S here, S accelerated and S here. So this is the acceleration. And you can see that the sort of in many cases, trying to accelerate actually slows us down. Right? So just adding too many things creates too large LTL instances, and the synthesis engines just choke.
finite-state or comparisons? What are you comparing to?
The same tools. So the same tools that work on infinite state. So, but these are just safety refinements, right? So you don't.
For the finite-state, you just compare to classical synthesis.
We didn't. Yeah. So. Yeah. So maybe I think Sean should be online. I think he actually. He may be able to confirm whether we tried this. But so. Yeah, I'll leave this. If Sean can join later, then he will answer that. Yeah, I think, so I think the main competition is essentially Reiner's tools, on which you will talk tomorrow. But their main problem here is that realizability works very, very fast, but synthesis fails in many of the cases, and we don't have a distinction between them. The LTL just becomes too big in many, many cases. So the LTL becomes big very, very fast. We have many, many propositions, and Strix chokes very, very fast. So one little note is that on some of these examples, there is real non-termination here, right? So all the other tools, they get real trying to enumerate an infinite state space. So this happens to everyone except us on these examples. I think I said that. Let me say a few things about future work, starting with a bit of theory. So yes, Zuk was there. So Balaban, Pnoeli, and Zuk show that this kind of refinement for model checking leads to relative completeness. And we know that this is not the case in general for us, but we still think that with some extension of our techniques, we may be able to get relative completeness. We know that we are incomplete because we handle very well loops where the environment wants to stay in the loop. If the controller wants to cheat and stay in a loop forever, we need to change the way we are handling the way we are handling things. And we know how to do it, but it will lead to formulas that have a very large number of disjunctions. And one of the main optimization of Strix is that they optimize each conjunct of a formula separately. And we think that if we try to feed it a huge formula that has a large number of disjunctions, it will be even worse, and we didn't even start doing this. Other theories, real arithmetic, we want to extend, but we haven't done that yet. One thing that I want to highlight is there's recent work by Irat Kalimov and Rudiger Erles, appeared in TACAS, where they represent a symbolic approach for LTL synthesis. So they use a chain of Kobuki automata in order to build a symbolic arena and analyze a symbolic arena. And unfortunately, they don't give strategies yet. They didn't implement the strategy extraction. But when we compare this to Strix on our example, synthesis is a lot faster. So a symbolic tool really, really helps us, but we can't use it completely. We can't replace Strix because we really need the strategies. We can't do anything without strategies. That's it. So I'm checking for input from my co-authors.
I think it would be, following up on my comment before, I think it would be really interesting to look at the kind of, if you have finite but getting larger arena, just seeing how it's scaled, just to feed it to synthesis tools versus trying to use this mechanism here of abstractions to deal with the growing size of the arena.
So
Part of what happened was, if you just take the arena and you just encode it in as a safety condition LTL, it will be you'll have an explosion there just because of the size of the arena.
Yeah.
And that's you might be able to outperform good synthesis tools when you focus on arena and scaling the arena, not the LTL necessarily, but the arena, the growth of the arena.
Yeah, so I agree, but the abstraction doesn't grow, right? So even if you say, okay, you didn't go far enough, right? So you went here to 3 bits, 4 bits, whatever.
Yeah.
We can go to any number of bits that still pass, and it has the same runtime. So in a way, there is something more that in this the liveness refinement gives us something that is additional, even for finite state.
Yeah.
So even if this is completely finite state and can be handled by normal tools, there is something here in the timing that tells us that there is something different.
So this is really interesting. What I'm
hold the mic close.
Is there a way for you to refine and get assumptions about liveness from the environment, right? For example,
yes, exactly. This is what we're doing.
How exactly do you do it? I missed this.
We're adding liveness assumptions on this environment.
Sorry, fairness assumptions.
We end up with a huge street game.
And so instead of doing synthesis and so on, if you went back to sort of the classical mutual exclusion or Paxos and so on, and just wanted to do verification of liveness there, in principle you could just use this for software verification for liveness, right? So, and maybe the environment is just the scheduler, and you have some fairness on the scheduler that it picks everybody. So,
but where is this?
So for example, I don't know of any software verification tool that can do automatic liveness verification for things like Paxos, right? And so in principle, all the things that you've said, that should be a special case, right? So maybe that gives you a set of benchmarks to look at.
I think we might be able to try. Again, using this kind of refinement for model checking, this goes back a long time ago, right? So 20 years ago, this was already suggested.
Okay, just very quickly. So I think there's already some work on extending. So for example, constraint horn clauses, basically like extending SMT constraint horn clauses. They were trying to extend. They were trying to encode some kind of synthesis, but with like weaker kind of strategies. Like for example, only safety. I think there's some work by Rybalchenko, and so there's quite a lot of works on that. And the theories can be like larger. I don't know if you looked at this, but
yeah. So Rybalchenko's tool no longer works, unfortunately. Rybalchenko's tool also requires a pretty extensive template of the solution. And then extensions of Rybalchenko's work that essentially use mostly SMT solver for solving these kind of horn constraints that lead to the formula, they miss this. So somehow there was progress on the SMT side, but the synthesis community that applies these techniques didn't harness this exactly in the same way that Rybalchenko did. Yeah, no, the framework should work, but sort of these are the implementations that are out there. It includes implementations that use this approach of translating this to horn clauses, giving and using quantifier elimination for getting essentially the programs and this is their performance. So these are not my tools.
Okay, let's thank Neil. Now, because we